Let us discuss here some difficult level questions. Here the first question is, in a solid state AB having the NaCl type of structure, the A atoms occupies the corners of the cubic unit cell, and if all the face centers along one of the axes are removed, then the resultant stoichiometry of the solid is. Now here, while doing this MCQs, we have to remember if AB is having NaCl type of structure. In NaCl, the ratio of Na is to Cl is 1:1. So the chloride ions forms the FCC. So if you talk about the chloride ions, it is having the FCC structure. So if you talk about FCC structure, let us assume this particular cube where the Cl minus are present at the corner as well as at the face center. These are the Cl minus ions only. Okay, and there are Na plus ions which will be going in the octahedral voids in the crystal of the Cl minus. So the octahedral voids over here are formed at the edge center of the FCC and at the body center position. So these are the Na plus ions. Now they are saying the AB is having NaCl type of structure. A occupies the corner. That means A is having position like Cl minus. So B will be having position like Na plus. Now they are saying if all the face center atoms along one of the axes are removed. So if you pass one axis like this and if you remove two face centers from this. So now that will affect the number of A. Now A is present at the corner, so that 8 into 1/8 they are as it is, but out of 6 there are 4 face centers are only left. So 4 into half. So this is 1 plus 2, that will make 3. And Na plus, that is B, are as it is. B is present at the edge center. There are 12 edge center, each contribute 1/4, plus there is one body center. So this is 3 plus 1, that is equals to 4. So A 3, B 4 is our answer. So option is option D. Next question, if NaCl is doped with 10⁻⁻⁴ mole% of SrCl2, the concentration of cation vacancies will be. Now if they are saying 10⁻⁴ mole%, that means when you have 100 mole of NaCl, it is being doped with 10⁻⁴ mole of SrCl2. That is, if you start with 1 mole of NaCl, that will corresponds to 10⁻⁴ upon 100, that is equals to 10⁻�6. So 10⁻�6 mole of SrCl2 is the concentration of cation vacancy. So if you convert this into actual moles, 1 mole corresponds to 6.022 into 10⁻23. So 10⁻⁻6 mole corresponds to 6.022 into 10⁻23 multiplied by 10⁻⁻6. So this comes out to be 6.022 into 10⁻17. Hence our option is option B. The packing efficiency of the two-dimensional square unit cell, which is shown, we have to find out. Now in this case, if you talk about the two-dimensional things, when we talk about a three-dimension, we talk about the volume. But when we talk about the two-dimensional things, we talk about the area. So if I have to calculate the packing efficiency, our formula should be the percentage area which is occupied by the atoms upon, we can say area occupied upon total area into 100. Now we have to talk about only this particular part. So when I'm talking about this particular part, the area occupied is this much by the atoms. Now this is 2 dimensions, so I can call this as one circle. This is 1/4 of the circle, this is 1/4, this is 1/4, and this is 1/4. So that makes one circle. So there are 2 circles. One circle is having the area of pi r square. So total that is area occupied, will be 2 pi r square, because there are two circles over here. Now when we talk about the total area, this is a square. If you talk about the edge length of this square is a, then this will be a square. But now the area occupied is in terms of r and this is in terms of a. If you look at this particular structure is nothing but kind of like a FCC. And for FCC, a is equals to 2 root 2 r. So if you substitute here, this is 2 root 2 r square. This is 4 that's 4 into 2, 8. That will be 8 r square. So now if I substitute here, area occupied is 2 pi r square upon 8 r square into 100. R square will get cancelled over here. So 3.14, that is 314 upon 4. That comes out to be 78.54%. So option is option D. Experimentally, it was found that the metal oxide has a formula M0.980. Metal M is present as M plus 2 and plus 3 in its oxide. The fraction of the metal which exists as plus 3 would be. Now if you talk about the metal which is total 0.98, it's actually existing in two forms. We have metal present in plus 2 form also and metal in the plus 3 form also. So let us assume that metal present in plus 2 form is X. So then definitely this is 0.98 minus X. Now when we have an oxide, the total of the oxidation state has to be equals to 0. So the first metal, it is in plus 2 state, its fraction is X, plus the second metal is plus 3 having fraction 0.98 minus X, plus there is one oxygen having oxidation state minus 2. This total has to be equals to 0. So this is 2X plus this multiplication will give you 2.94 minus 3x minus 2 is equals to 0. So if you'll find this is 0.94 is equals to x. So if x is 0.94, the plus 3, metal plus 3 percentage will be 0.98 minus 0.94, that is 0.04. Now if you have to calculate the metal percentage of plus 3, so plus 3 exists as 0.04 divided by total is 0.98 into 100. So this is around 400 divided by 98. That comes out to be around 4.08%. So answer is option B. Our next question is, which one of the following pair of the solution will be isotonic at the same temperature? Now when this kind of the electrolytes with their concentrations are given, we have to find out their actual concentration by multiplying the number of cations or anions formed with their concentration. For example, if we talk about AlCl3, the AlCl3 will give us the 4 ions. So 4 into 1.5, that makes 6. Similarly, Na2SO4, that will make 3 ions multiplied by 2, total 6. So here the concentrations are same, and when the two solutions have the same concentration, they will be isotonic with each other. Hence our option is option A. 10⁻³ molar solution of PtNH3 4 times Cl2 in water shows depression in the freezing point by 0.0056 degree. The structure of the compound that we need to find. First of all, depression in freezing point, that is delta TF, is equals to I into Kf into molality. Now I have taken here I because this kind of the substance which is given over here is electrolyte. Now depression given is 0.0056, that is equals to, we need to find the value of I into 1.86 into 10⁻⁻3. If you calculate this, you will get the I around 3. So if I'm getting the I around 3, that means after dissociation of this complex, we should get the 3 ions. So the one which can give us the 3 ions is option C, because if you'll dissociate this, you will get 1 coordinate ion plus 2 chlorine ions. Total 3 ions you are expecting here. Hence our option is option C. The freezing point of the solution containing 36 grams of the compound having empirical formula CH2O in 1.20 kg of water is found to be minus 0.96 degrees Celsius. The molecular formula of the compound we need to find. Now here they have given us the freezing point of the solution. So from the freezing point of the solution, we can find the depression in freezing point. That's the actual the freezing point of the water, that is 0, minus of the solution, that is minus 0.93. So that is equals to 0.93 degrees Celsius. Now we have a formula delta TF is equals to Kf into molality. Right now they have given us the data for the calculation of molality. So I'm writing the formula of molality, that is mass of the solute divided by molecular mass of the solute into weight of the solvent in kg. So now in this case we need to find the value of M2. So M2 will be equals to Kf, that is given 1.86 into 36 gram of the substance is provided, divided by this delta TF will come here, so 0.93 multiplied by the substance which is given is 1.2 kg. So now if you multiply this, you are expected to get the answer 60. Empirical formula is given to us, that is CH2O. So if we'll calculate the empirical formula mass, carbon is 12 plus hydrogen is 2 here and oxygen is 16. So total comes out to be 30. So if I'll calculate the molecular weight divided by the empirical weight, I'm getting the answer 2. So empirical formula is to be multiplied by 2. Empirical formula is CH2O to be multiplied by 2. So answer is C2H4O2. That's a molecular formula of the compound. So C2H4O2, that is our option B. The next question is 17.4% mass per volume of K2SO4 solution at 27 degrees Celsius is isotonic with 5.85% of mass per volume of NaCl. If NaCl is 100% ionized, the percentage ionization of K2SO4 that we need to find. Now if you talk about the K2SO4, when it will dissociate to give us twice of K plus SO4 2 minus. Now when this will dissociate, let's say we are starting with initial condition 1, the dissociation will be 0. But out of 1, if alpha will dissociate, I'll get 2 alpha of this and alpha of this. So total moles is 1 minus alpha plus 2 alpha plus 2, that is alpha, that is 1 plus 2 alpha. So therefore we have I is equals to 1 plus 2 alpha. So in this case, if I am calculating the osmotic pressure, that will be equals to I into CRT. Now I here we are getting 1 plus 2 alpha into bracket. Now when we calculate the concentration of this, they are saying it's 17.4% of solution, which is taken over here. So this is divided by 100 multiplied by its molecular weight of K2SO4 is 174. Multiplying this by 1000 RT. So if you calculate this, this will entirely get cancelled. So I'll get 1 plus 2 alpha into RT. So this is for K2SO4. Similarly, when you will calculate for NaCl, it will dissociate to give Na plus and Cl minus. So 1, 0, 0 for initial condition. 1 minus alpha will give alpha of this, alpha of this. So I will be equals to 1 plus alpha. Similarly, if I calculate pi 2 I into CRT, that is equals to 1 plus alpha into the percentage given over here is 5.85 divided by 100 multiplied by 58.5 into 1000 RT. So that is, if we'll calculate this, we are going to get the answer here 2 RT. So here we have got the answer. This is 2RT just because I just missed one point over here. This is 1 plus 1. Alpha is 100% given here. So this is 2 given. So that's why this is 2RT. Alpha is I is equals to 2 here. But here they have given pi 1 is equals to pi 2. Therefore, 1 plus 2 alpha RT will be equals to 2 RT. RT gets cancelled. Here we'll get 2 alpha is equals to 1. So alpha is equals to 0.5, that is 50% dissociation we are expecting for the K2SO4 solution. And electric current is passed through the silver voltmeter connected to the water voltmeter. The cathode of the silver voltmeter weighed 0.216 gram, more than the end of the electrolysis. The volume of oxygen that is formed at STP that we have to find. Now here, this is according to Faraday's second law of electrolysis, that weight of the silver which is deposited divided by the weight of the oxygen which is produced will be equals to the equivalent weight of Ag divided by equivalent weight of that oxygen. Now we are getting the amount of silver deposited is 2.1216 divided by the amount of oxygen that is produced, that is to be calculated. Let us assume it as X. Equivalent weight of silver is 108 and that of oxygen is 8. So when you will calculate the value of X, you will get the answer 0.016 gram. Now we know that 32 grams of oxygen, that is corresponds to 22,400 centimeter cube. So 0.016 gram of oxygen will be 0.016 multiplied by 22,400 divided by 32. So it has to be half of the almost amount. So it is 11.2 centimeter cube should be the expected answer. So our answer is option B. A rod of cobalt metal was placed in the solution containing Ag plus, Fe3 plus, Cu2 plus. We have Ag plus, Fe3 plus and Cu2 plus at 1 molar concentration each. If E0 of silver, which is given silver to silver, Ag plus to silver, which is given 0.799, Fe3 plus to Fe2 plus change is given 0.77. Then we have Cu2 plus, which will change to Cu, which is 0.34. They have given few other electrodes also, like Fe3 plus to Fe, which is minus 0.04, and Cu2 plus to Cu is 0.133, and cobalt, that is Cu2 plus to Co, that is to be given, that is 0.28. Then the solution will contain. Now first of all, if we talk about the cobalt metal, the cobalt metal is being dipped in that solution. So we are expecting the reverse of this, and if it is reverse of this is expected, so the potential will make a reverse, that is minus 0.28. So if I make it minus 0.28, then all these potentials are higher than the cobalt, and that's why cobalt will be able to reduce all of them to the respective product. Hence, at the end of the reaction, we are expecting silver should be there, Fe2 plus should be there, copper should be there, and the cobalt should turn to the cobalt 2 plus. So we are expecting 4 products in this reaction. So we are having Fe2 plus, copper, silver and CO2 plus. Hence our option is option D. At 25 degrees Celsius, the molar conductance at infinite dilution for strong electrolytes NaOH, NaCl and BaCl2 are respectively given. We need to calculate for BaOH twice. So this is one of the applications for the Cauchy law. If I have to calculate the molar conductivity for BaOH twice, then I can add the conductance of BaCl2. So I'll add the conductance of BaCl2 plus I will add NaOH. But since in the required equation I need OH twice, I will multiply the conductance of the NaOH by twice. So this is NaOH, and I will subtract the chlorine from this. So twice of Cl2. So twice of NaCl conductance has to be subtracted. So this NaOH, which is given to be, first we'll calculate for BaCl2, which is given to be 280 into 10 raised to minus 4, plus this is 2 into, for NaOH is 248 into 10 raised to minus 4, minus this is 2 into 126 into 10 raised to minus 4. So if you calculate this, the answer comes out to be 524 into 10 raised to minus 4. So our option is option C. For the cell M plus 2 saturated solution of sparingly soluble salt MX2 is in salt bridge combination with M plus 2 having 0.001 molar concentration, having metal M. The EMF of this cell is 0.059. We have to calculate the KSP for the MX2. First of all, over here, if you talk about this anode, we are having M, it's turning to M plus 2. So anode reaction is metal is losing 2 electrons so as to become plus 2. While at the cathode, plus 2 is becoming metal. So M plus 2 is gaining 2 electrons to become M. So overall net reaction, if I'll find, there is M plus 2 which is of cathode, it's turning to M plus 2 which is of anode concentration. So if I'll calculate, if I use the Nernst's equation, E is equals to E0 minus 0.059 upon 2 electrons are exchanged over here, log of metal plus 2, that is having anodic concentration, upon metal plus 2 with the cathodic concentration. This is given to be 0.059 minus, here the E0 of this cell is 0, minus 0.059 upon 2 log metal concentration, anodic concentration that we have to calculate, divided by cathodic concentration, which is given to be 10 raised to minus 3. This calculation MX2 saturated solution, that is to be calculated. So if we'll do this calculation, this will get cancelled. So we'll get minus 2 is equals to 3 log concentration of M plus 2 at the anode. So concentration of M plus 2 at the anode is equals to 10 raised to minus 5. Now when I talk about the salt MX2, that will dissociate as M plus 2 twice of X minus. So we'll consider the solubility of metal is S, this will be 2S. So KSP, if I have to find, it's a concentration of M plus 2 into concentration of X minus square. So this is S, while this is 2S square. So this comes out to be 4S cube. But S is 10 raised to minus 5, that is cube. So 4 into 10 raised to minus 15 is our answer. Hence our option is B. For the reaction N2O5, it's turning to twice of NO2 plus half of O2. The respective reactions are given. If you talk about, it's minus D N2O5 upon dt is equals to K1 N2O5. Then we have D NO2 upon dt is equals to K2 into N2O5. While next is, if we talk about, it's d O2 upon dt is equals to K3 into N2O5. If we'll talk about from the equation, if I'll write the rate law, there should be minus d N2O5 upon dt is equals to half of d NO2 upon dt, that's equals to, it's always twice of dO2 upon dt. So if I'll compare this with the respective equation, there should be K1 as it is. But now this is twice, so I'll multiply the entire equation. This is equals to K2, this is equals to K3. But this is half and this is twice. So if I'll multiply the all equation by 2, So K1 will be multiplied by 2. 2 will get cancelled and here it will be 4. So twice of K1 will be equals to K2, that is equals to 4 of K3. Hence our option is option B. Choose the reaction scheme for the which the plot of the concentration against the time is given below. If you look at this particular reaction, the P concentration is decreasing, Q concentration initially it is increasing and then it is decreasing, and this has to be the graph of the R, which is continuously increasing. That means initially the P is decreasing, which is turning to Q, and since Q decreases it turns to the R. So this reaction scheme should be P turning to Q and Q turning to R. So option is C. The rate of decomposition of ammonia is found to depend upon the concentration of ammonia as per the equation. When the concentration of ammonia is very high and very low, the order of the reaction will be. If you talk about this equation, we have minus D NH3 upon dt is equals to, I'm just dividing the entire equation by concentration of ammonia. So I'll get K1 upon 1 upon NH3 concentration plus K2. So let's say when NH3 concentration is very high. When it is very high, 1 upon NH3 is very low. When 1 upon NH3 is very low, it can be neglected in front of K2. So here the rate of reaction will be K1 upon K2, that is in short K. Since rate is dependent on only K, not the concentration of ammonia, this reaction has to be 0 order. But when ammonia concentration is low, 1 upon NH3 will be very high. If 1 upon NH3 is very high, the K2 can be ignored. So if K2 can be ignored, the rate will be K1 upon 1 upon NH3 concentration. So that is equals to K1 into NH3. So this is depending on the concentration of ammonia. So this has to be first order. So answer should be 0 and 1. Hence our option is option C. Next question is, a substance undergoes the first order decomposition. The decomposition follows the two parallel first order reaction. That is, A is decomposing to B with the constant K1 and decomposes to C with the constant K2. We have to find out the percentage distribution of B and C. First of all, if I have to find a percentage distribution of B, let's say, so percentage of formation of B will be equals to, B is following the constant K1. So K1 divided by, it's divided into two roots. So K1 plus K2. So we are calculating kind of like a fraction into 100. So K1 is given 1.26 into 10 raised to minus 4 divided by 1.26 into 10 raised to minus 4 plus 3.8 into 10 raised to minus 5 into 100. So it's 1.26 into 10 raised to minus 4. We can make this 10 raised to minus 4. So it's 1.26 plus 0.38, and we can take 10 raised to minus 4 common from this. So after calculation of this, we'll get the answer 76.83%. So if this is 76.83%, you can subtract this number from 100 to get the percentage of C. Anyways, our answer is matching with the option D. So answer is option D. General principle. The correct statement amongst the following is, here option A, the hydrogen is used to reduce nickel oxide. Nickel oxide can be reduced by the hydrogen. There are some metals like copper, nickel, we can reduce them with the hydrogen. Zirconium is refined by the Van Arkel process. Yes, because we can convert the zirconium into their volatile complexes. Sulfides are the galena. It's concentrated by froth flotation. Yes, galena is PBS, which is a sulfide ore. Hence, we can concentrate it by the froth flotation process. In the metallurgy of iron, the flux used is silica. This is the wrong statement, because in the metallurgy of iron, iron is generally extracted from the hematite ore, and in hematite ore there is gangue, which is silica, and this particular gangue is removed by adding flux limestone. So calcium carbonate is used as a flux in the metallurgy of iron. So our option is option D. The next question is, we have a Ellingham's diagram over here. On the basis of the figure, choose the correct option of the temperature at which the carbon reduces FeO to iron and produces carbon monoxide. Let us highlight the graphs of the FeO, which is to be reduced, with the help of the carbon monoxide. So if you can see, both this particular plot intersect at point A. So after the temperature, after this particular point A, we can see the delta G value of carbon monoxide is becoming negative and delta G value of carbon FeO is becoming positive. That means reduction of FeO by the carbon monoxide is possible only above the temperature at the point A. So if you'll find, the option is D, that is above the point A, we can reduce the FeO to Fe using carbon monoxide. Which of the following extraction process is not correctly matched? Carbon reduction possible for the carbon. Yes, copper oxides can be reduced by the carbon. Lead self-reduction. Lead sulfides are very unstable. So when lead sulfides are oxidized, it turns to the lead oxide. While this remaining sulfide reacts with each other, self-reduction takes place to give Pb and SO2. Electrolytic reduction for the aluminium because it's highly electropositive metal. Complex formation metal for the magnesium. This is not possible because this is the hydrometallurgy process where we use the water as a solvent. And the metals like magnesium, sodium, they are highly electropositive metals. They have to be purified by the electrolytic refining, not by the complex formation. Hence, our option is D. In the process of extraction of gold, this roasted gold on treatment with the cyanide ions, it forms a complex X. First of all, if you talk about the gold, it is having the coordinate valency twice. So the gold has to be complexed with the cyanide. Gold has to be complexed with the cyanide ion twice. The gold is having plus charge and cyanide is -2. So there will be minus charge on this. And when it is forming a complex with the zinc, when it is allowed to react with the zinc, zinc replaces the gold. Zinc is having coordinate valency of around 4. +2 zinc with the cyanide 4-. So there should be charge on the complex 2-. So X should be this and Y should be this. So our option is option A. At what temperature a reaction will be at equilibrium at 1 atmosphere if delta H and delta S are given over here respectively? These values do not change with the temperature in any significance. Now, when I'm talking about the delta H, delta S calculation, the delta G is equals to delta H minus D delta S. Now, when this is an equilibrium condition, the delta G is equals to 0. And therefore, the temperature can be calculated by just dividing the delta H by delta S. Now, the delta H given over here is 30.58. This is in kilojoule. So, I'm multiplying this by 10 raised to 3 divided by 66.1. This value is in joule. So, when you divide this, you will get the answer 462.6 Kelvin. Hence, our option is option B. With respect to the figure given below, the correct statement is, we will talk about if this particular reaction, if we'll check. Now the reactant is having this comparatively energy. If you compare, the reactant is having more energy compared to the product. So the forward reaction is having the less amount of energy compared to the backward reaction. Therefore, if you talk about the delta U, that is delta U is to be calculated for forward reaction, that is changing from B to A. So B minus A, that is energy B minus energy B, A, that will be delta U for the forward reaction. So our option is option B. Again, I'm repeating, this is the enthalpy change for the product. This is the enthalpy change for the reactant. So this is B, this is A. So delta U will be B minus A. The equation half of H2 plus half of Cl2 is giving HCl at 298 Kelvin. It's 22.60. What this equation is indicating, generally the heat of absorption which is given, it stands for the 1 gram equivalent. So we'll read the option. The heat absorbed when 1 gram molecules of HCl is formed. This is 1 gram molecule. It has to be 1 gram equivalent. It is positive. The heat absorbed is absolutely right, but it is gram molecules written. So option A is not a right answer. Here it is heat given out. No, delta H is positive, so heat is not given out. C option, heat absorbed when 1 gram atoms. 1 gram atoms is not the correct answer. Option D, heat absorbed when 1 gram equivalent of the HCl is formed from its elements. So our answer here is option D. An athlete is given some glucose of energy equivalent to 880 kilojoule. Now he utilizes 50% of this gain energy in the event. So if we have 880 kilojoule energy with the athlete, 50% of this is utilized, that means around 440 kilojoule. In order to avoid the storage of the energy in the body, the weight of the water he would need to specify is. Now if you talk about the heat of evaporation given over here, 44. That is indicating 44 kilojoule corresponds to the 1 mole. So we have 440 kilojoule, so that will corresponds to 10 mole. If I talk about 1 mole of water, that's equals to 18 grams. So 10 mole corresponds to 180 grams. So answer is option D. When 0.01 mole of cobalt complex is treated with the excess of the silver nitrate solution, 4.305 gram of silver chloride is precipitated. The formula of complex we need to find out. First of all, if the silver chloride is silver AgCl. Silver is having 108 mass plus 35.5. So this comes out to be 143.5. So if we'll calculate the number of moles which is deposited for the silver chloride, so 4.305 divided by 143.5, the answer comes out to be 0.03 mole. That means 1 mole of this complex is depositing 0.03 moles of Cl minus. That's indicating there should be 3 chloride ions outside the bracket. Hence our option is option C, having 3 Cl outside the complex, giving 3 Cl minus ions. Two isomers X and Y with the formula CrH2O5 times ClBr2 were taken for the experiment on depression in the freezing point. It was found that 1 mole of X gave the depression related to 2 moles and 1 mole of Y gave the depression related to the 3 moles of the particles. What is the structure of the complex that we need to find? So if you talk about the complex over here, first is giving related to 2 moles. That means this complex should break to give 2 ions only. So X should give 2 ions and Y should give 3 ions. Now if I talk about the 2 ions and 3 ions, then we have option D. If I talk about option D over here, we have this particular complex and the Cl minus will be formed. So 2 ions will be formed here. While here we have 1 complex and 2 bromide ions. So there will be 3 ions formed. Hence our option is D. 0.02 mole of CONH3 5 times Br Cl2 and 0.02 mole of CONH3Cl SO2 are present in 200 cc of solution X. The number of precipitates Y and Z that are formed when the solution X is treated with the excess of silver nitrate and excess of barium chloride. Now when you put silver nitrate, silver will precipitate the Cl minus and barium chloride will precipitate the SO4 ions. Now, if we are allowing this to react with this silver chloride, there are two silver ions are there. So 0.02 of the complex this will give twice of silver chloride. So we are expecting silver chloride 0.04 mole formed. So Y complex should be 0.04 and Z complex which is formed, barium chloride which is treated, barium will react with 1 mole of SO4 only. So 0.02 will give you 0.02. So 0.02. So answer should be 0.04 and 0.02. Hence our option is option D. The correct electronic configuration for the complex Mn H2O 6 times SO4 we have to find. First of all, Mn is having atomic number 25. So it's argon 3d5 4s2. In this, Mn is present in +2 oxidation state. So we have 3d5 configuration. In this 3d5 configuration, we have 5 unpaired electron of this. 4p is empty. 4s and 4p will be empty. Water is a weak field ligand and therefore we are expecting the hybridization will be sp2 hybridization. So these unpaired electrons are not affected. But when this octahedral complex will be formed, there are 3 T2G down and EG up. Since the gap is very small, we are having sp3 hybridization, and hence the electron after filling in these 3 orbitals will go up and go single over here. So it is like T2G 3 and EG is occupying 2 electrons. Hence our option is option A. The halogen derivative of X on treatment with zinc hydrochloric acid give the hydrocarbon with the 5 carbon atoms in the molecule. So we are having halogen derivative, that is chloro derivative, that is X. This is on treatment with zinc HCl. This is a reduction reaction which is giving the hydrocarbon containing 5 carbon atoms. So this is hydrocarbon when we are getting 5 carbon containing hydrocarbon. When X is dissolved in ether and treated with the sodium, X is dissolved in ether and treated with the sodium. This is a condition kind of like a Wurtz reaction. It's giving us 2,2, 5,5 tetramethyl hexane. It's containing hexane. So let us draw 6 carbon atom. 1, 2, 3, 4, 5, 6. This is 2,2 tetramethyl. So 2,2 here 2 methyl and 5. 1, 2, 3, 4, 5. So 5. This is hexane is formed as a product over here. So when I'm talking about this particular reaction, we can find the halogen derivative, but just by dissociating, because Wurtz reaction gives us the alkane which is containing double number of carbon atom compared to the haloalkane. So we can think like this: CH3, 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 so CH2, Cn. So if you reduce this also, we'll get the hydrocarbon which is neohexane containing 5 carbon, neopentane which is containing 5 carbon atom. So our answer is option C. We are having 1 chloro 2,2 dimethyl propane. Question number 2. A dihalogen derivative X of hydrocarbon containing 3 carbon atoms reacts with alcoholic KOH to give another hydrocarbon, which gives red precipitate with ammonical copper chloride. X gives the aldehyde when treatment with the aqueous KOH. Now if we'll talk about this particular reaction, first of all we have a dihalogen derivative. This is X having 2 halogen groups. This is containing 3 carbon atom. Now when we talk about the 3 carbon atom, this is on treatment with the KOH, that is giving us the hydrocarbon. So now if you have dihalogen derivative with the 3 carbon atom, it may happen that 2 halogens should be attached at the terminal, or it should be attached at the non-terminal carbon atom. So this is having 3 carbons. So there are 2 possibilities of this structure. If you allow this to react with the alcoholic KOH will remove this HCl and you will get the corresponding alkene. This further on treatment with ammonical copper chloride, you're expected to get the red precipitate. Now this gives X gives aldehyde on treatment with aqueous KOH. Now if you are getting aldehyde on treatment with aqueous KH, it has to be terminal, because if you allow this to react with terminal, let's say this is the reactant, if you allow this react with the alcoholic aqueous KOH, you will get CH3, CH2, CH, both these replaced by OH, but this will undergo the water removal so as to give the corresponding aldehyde. But if you allow this to react with the non-terminal always gives us formation of ketone. So the starting material has to be 1,1. So our option is option B, 1,1 dichloropropane. An alkyl halide with the molecular formula C6H13Br on dehydrohalogenation give two isomeric alkane X and Y with the molecular formula C6H12. On reduction, the ozonolysis, X and Y gave four different compounds. The alkyl halide is. Now, if I'm talking about this particular reaction, first of all, we'll concentrate only on the ozonolysis part. If I talk about the ozonolysis, we have X and Y, which is having formula C6H12. This X and Y being obtained from the C6H13Br by the dehydrohalogenation. Two isomeric compounds we are getting. Now this is giving us the formation of CH3COCH3, CH3CHO, CH3CH2CHO, and CH3 twice CHCHO. Now these are having 3 carbon. These are having 2 carbon. These are having 3 carbon, and 1, 2, 3, 4. These are having 4 carbon. So we can make a combination which will give us the formation of total 6. So we can make a combination of these two, and we can make a combination of these two. So if I make a combination of these two, we can think about the alkene by just removing the double bond O from this. So if I remove the O from this, we should get CH3, C, CH3. I'm removing oxygen from this. I'm writing double bond. Remove the oxygen from this also. So we'll have C, CH2, CH3, and this is H. Okay. Similarly, we can make a combination of this CH3, CH. Remove the oxygen from this. Double bond CH, CH, CH3 twice. If this particular alkenes are being obtained by the dehydrohalogenation, so you can add HBr to this. So if you add HBr to this, we are expected to get 1, 2, 3, 4. If I number this is 1, 2, 3, 4, and 5. So if we can add the HBr to this particular compound, so we can add HBr to this particular carbon, and because this is having the less number of hydrogen, and we'll give H to this. So if I number this is 1, 2, 3, 4. So this is kind of like 4 bromo, 2 methyl. It's a pentane type of compound. So our option is over here. If I talk about HBr is added over here, we can add HBr. So it's Br is added here and H is added here. So 1, 2, 3. So if I number the chain from here, so it will be third carbon is containing bromine. So it's 3 bromo, 2 methyl pentane. So our option is option D. Again, I'm repeating. This C6H13Br is dehydrohalogenated so as to get C6H5. We are getting 4 different compounds. So if I want to make it having the same molecular formula, they should contain, both of them should contain the 6 carbon. If you look at the product, there are containing 3, 3, 2 and 4 carbon atoms. So I made the combination of 2 and added HBr to that. So when I'm added HBr, it's giving me the product 1, 2, 3, 3 bromo, 2 methyl pentane. So this particular reaction is giving option D. Question number 4. The correct order of increasing the reactivity of CX bond towards the nucleophilic substitution reaction. Now, if I talk about the nucleophilic substitution reaction, here there is a halogen, aliphatic compounds. Nucleophilic substitution reactions are always reactive towards the aliphatic. So we have two aromatic and two aliphatic compounds. So out of two now aliphatic compounds, the one with the tertiary group are more reactive compared to the secondary. So third compound is more reactive compared to the fourth compound. Now let us talk about the compound number 1 and 2. When I'm talking about 1 and 2, it has been seen that the halogen derivative compounds are less reactive, but we can increase their reactivity by attaching the electron withdrawing group at ortho and para position. So compound 2 has to be more reactive compared to compound 1. So if we look at this particular answer, our answer is option C. Next is the C3H7OH alcohol is on treatment with the concentrated H2SO4 at 443 Kelvin. So we are expecting the formation of alkene in this case. So C3H7OH will give us formation of alkene, that is propene. So compound A is propene. This is on treatment with Br2. We'll get the dibromo compound. So CH3, CH, CH2. We'll get the dibromo compound here. This is compound number B. This is on treatment with excess of alcoholic KOH. So we'll allow this to react with excess of alcoholic KOH. First KOH will remove the HBr. Will give us formation of CH3, CH, CH2, Br with a double bond. CH double bond CH2Br, and then followed by, if I talk about the second HBr removal, will give us the triple bond. So CH3C triple bond CH. So our option is option C. The compound given on treatment with the KMNO4 in alkaline medium. So in alkaline medium, if I talk about this particular reaction, this particular alkaline KMNO4 will carry out the oxidation of all these groups. So first of all, when the oxidation will take place, this particular alcoholic group, secondary alcohol, will turn to the ketone. As well as we have a double bond over here. This double bond will also turn to their corresponding oxides. So we are expecting the individual ketone formation at this point of alkene. So our option is option C. The product of the following reaction we have to find here. Now here we have OH at this particular position and PBr3 is the brominating agent. So if PBr3 is the brominating agent, we are going to get the replacement of OH by the Br. So here the option is B, without affecting the double bond. The next question is an ether, that is C6H14O, when treated with the excess of the concentrated HI produced two alkyl halide, which on hydrolysis gave the compound B and C. Oxidation of B is giving the formation of the acid, and whereas oxidation of C is giving the formation of the ketone. The product D and E which are formed, that we have to find. So there is C6H14O. This is formation of ether. This is compound A. This is on treatment with concentrated HI, is giving us the formation of B and C. Now this compound B, which on oxidation is giving us formation of acid. This is compound D. While C is on treatment on oxidation is giving us the formation of the ketone. So this is compound E. So definitely on treatment with the concentrated HI, this is hot concentrated HI, if you are getting the formation of acid, the B has to be primary alcohol. And if the compound C is formed, this has to be secondary alcohol, because on oxidation the primary alcohol turns to the acid and the secondary alcohol turns to the ketone. So if this hot concentrated HI is giving us the formation of the equal number of the acids and the ketone, then we are expecting the product has to be B, that is acetic acid has to be formed, and the ketone, that is acetone, has to be formed. So in overall option we are getting option B here. Our next question is, in the following reaction, the acetaldehyde is oxidized, followed by its reaction with PCl5 gives the compound B, KCN gives C, and acid hydrolysis gives D. We have to identify the compound D in this reaction. So when we talk about acetaldehyde, this is CH3CHO. This is on oxidation. We are expecting the formation of the carboxylic acid. So we'll get the compound A, acetic acid. This is further on treatment with PCl5. PCl5 is a chlorinating agent, replaces OH by Cl. So we'll get CH3, C double bond O, Cl, followed by its reaction with KCN, cyanide reagent. So we'll get CH3, C double bond O, Cn, which is on acid hydrolysis will give us CH3, C double bond O. This will become COOH. This particular compound is malonic acid. So our option is option C. The product P in the following reaction we need to identify. This is a particular compound where we have the aromatic cyanide with OCH3. This is on treatment with the Grignard reagent CH3MgBr. So when the Grignard reagent addition will take place, the Q compound will be like this. So this is between this, the carbon is positive and nitrogen is negative. Magnesium is positive and carbon is negative. So carbon will go to the CH3 will go to the carbon. So CH3 will be here. This will be double bond N MgBr. This is further on hydrolysis will give us the formation of corresponding ketone. So without affecting this particular OCH3 group, hence our option is option D. In the following reaction, the sequence, the correct structure of E, F and G, we can see here this is kind of like a malonic acid which is on heating giving us compound E. This is I2NaOH, that's a condition for the iodoform test giving F and G. This asterisk implies the 13C labeled carbon is present. Now when you heat the malonic acid will turn to the corresponding ketone. So our compound is E is the ketone. This is on further treatment with I2NaOH. This is the iodoform test. So we'll get the corresponding, the breakage will take place here and we'll get corresponding iodoform here. So it will be CHI3 formation and plus we'll get formation of this corresponding salt of this acid. So C double bond O Na. So our products are, if we match with all of this is option C. Question number 5, the aldehyde that do not undergo the aldol condensation. The condition for the aldol condensation is the one which is having the alpha hydrogen atom will undergo the aldol condensation. If we talk about the compound propanol, it's propanol, so it's CH3, CH2, CHO. This particular compound is not having the alpha hydrogen atom, so it will not give the aldol condensation. So option 1 is valid. Then 2, we have trichloro, it's ethanol, so it's CCl3CHO. Definitely this is also not having the alpha hydrogen atom. Then methanol, it's HCHO, so this will also not give us. The ethanol, it's CH3CHO, this is having alpha hydrogen, so this won't give. And the benzaldehyde, so benzaldehyde it's CHO, so it won't give the test with, that is aldol condensation. So overall if we'll find the compound which is not having alpha hydrogen atom is the 2, 3 and definitely 5. So this is 2, 3, 5. So option is D. Which compound amongst the following gives a positive iodoform test? The iodoform test is given by those alcohols or the aldehyde ketone which are having CH3 groups besides the functional group. So if you talk about the first compound, that's ethanol. Ethanol is CH3CH2OH. The carbon bearing OH is having CH3 group besides this, and therefore we are expecting 1 will give the test. Then the next one is ethanol. Ethanol is CH3CHO. So the carbon bearing functional group, besides that we have CH3, so this will also give 1 butanol. So 1 butanol is CH3, CH2, CH2, CH2OH. So the one carbon which is bearing OH is not having CH3 besides, so it won't give you the iodoform test. The next one is 2-butanol. So it's CH3, CHOH. So definitely this is having the CH3 group besides the functional group containing carbon. So this will give the test. So overall we have got the answer here. It's 1, 2 and 4. So our option is option D. The major product of the following reaction is, if we can see, this is a kind of phthalimide which is on treatment with KOH, that will form a potassium salt, and potassium salt will be formed like this. This will be minus and K will be plus. If you allow this to react with any halide compound, CH2Cl, obviously the aliphatic group will react with this. So Cl will react with K so as to form the KCl, and we'll get formation of this will be NCH2Br. Hence our option is option A here. In the reaction given, there is a kind of amide compound which is on treatment with NaOH-Br2. This is Hoffman's bromamide degradation, and Hoffman's bromamide degradation will give us the corresponding amine which is containing one carbon less. So this will turn to the amine by the loss of this carbonyl group. This is further on treatment with, this is benzoyl chloride. So if you'll allow this to react with benzoyl chloride, there will be HCl removal over here, and we'll get formation of, this is CH3, this will be NH, C double bond O, and simply benzene ring. So our option is option C. Aniline in the set of following reaction yield the colored compound Y. So if you allow this aniline to react with a diazonium salt, so we'll get a diazonium salt formation over here. So that is X. This is on treatment with, this is N, N dimethyl aniline. So when the diazo coupling will take place, this benzene ring with N double bond N will be attached to the para position of this. So N CH3 CH3. So like this we have option C. Aniline on treatment with NaNO2. So aniline when on treatment with NaNO2 and HCl, this will give us formation of the diazonium salt. This gives the compound X. This is compound X, which on treatment with the cuprous cyanide. So if we'll allow this to react with the cuprous cyanide, it will cause the cyanation, so we'll get cyanobenzene. That gives another compound Y. So this is compound Y. This is Y on treatment with H2 nickel. This is giving compound Z. This is reduction reaction, and reduction will give us corresponding amine. We need to find a compound Z. Z is benzyl amine. Hence our option is option B. The product C in the following reaction we have to find. So first of all, aniline on treatment with Br2 in alkaline medium. So aniline is ortho and para directing. So bromination will take place at ortho as well as para position. This is on treatment with NaNO2 with HCl at 0 degrees Celsius. Will give us the diazotization. Diazonium salt is obtained here, and this is further on treatment with HbF4 heating. This diazonium group will be replaced by fluorine. Hence our option is option D.